Now let's look at torques in static situations. So statics is when there's no motion, so that would mean all forces are balanced. If all forces are balanced, it can't rotate either to be static, so all torques must be balanced. Now, if I apply a force here, for example, it's going to do two things. It's going to try to rotate that object. It's also going to try to move the object down that way. Now, the pivotal point is fixed, so it prevents any motion that way. So what that pivotal point's got to do is essentially is providing a force in the opposite direction to that to stop that object from moving down. We're not going to look at the force on that pivotal point. We're just going to look at the torques, and I hope you understand that if I'm looking at that pivotal point there, the perpendicular distance to the point is 0, so therefore whatever force is applied to it, the torque is 0. So we don't have to work with that force on that pivotal point to balance the torques. Okay, we can start. Okay, let's apply a force of F1, let's say 100 newtons. There's 100 newtons. How am I going to put the static? Well, quite obviously, I will have to put a force in the opposite direction to make it static. If I go directly underneath it, so the same perpendicular distance, then that force would have to be 100 newtons as well, and therefore any force rotating the object clockwise is equal to any force or torque rotating it counterclockwise, and it doesn't rotate. I want to be a little bit more interesting. Let's define another force F2, which is what we want to work out. And we've got to assign distances, obviously, otherwise we can't work anything out. So, look, let's call that distance 1 is 20 centimeters, and distance 2, let's make it 8 centimeters. So the question is, what force is required at 8 centimeters to keep this object from rotating, given that this force is applied for 100 newtons at 20 centimeters? Now, a couple of things we do just to make sure the communication's right. We first of all define a direction as being positive. I normally say clockwise is the positive direction. So any torque making a clockwise motion is positive, any torque making it counterclockwise is negative. So the next step is to provide a statement. So the statement is going to be that the sum of all torques is equal to 0. Now what does that mean? Using our positive and negative things, it means we have torque 1. Now here we can say plus and then work out that's going to be minus, but already we know that force 2 is going to make a negative direction, is going counterclockwise. So let's put it negative right from the word go. So torque 1 minus torque 2 is equal to 0. Look, just putting our working over here so we get a bit more working space. What that obviously means is torque 2 equals torque 1, that's what we expected. Now we have F2 times D2 equals F1 times D1. Let's define a little bit more working space over there. We're after finding the force 2 to balance it, so let's bring the D over the other side, so it's F1 D1 over D2, and that equals 100 newtons. Now if we wanted to work in terms of SI units, we should make them all the distances in meters, but we can get away with it here because we've got a division there, so dividing by 100 here, cancelled out by dividing by 100 there, so let's just keep it in centimeters. Okay, so it's 100 times D1 over D2, which is 8, and the force required to do that is 250 newtons. Okay, and that's what we expected to be bigger. 100 newtons there. On the inside, it takes more force to try to turn an object, just like a lever. Smaller distance, the more the force required. If it was halfway, if it was 10 centimeters, well, the ratio between the distances is 10 is to 20, or it's going to be a half. So we'd expect twice the force to stop that from rotating. just to double check to make sure we're on the right track. Okay. It does get a little bit more complicated when we start putting forces on angles, but again, it's just a matter of working out components first, and it's not too difficult. That's the basic.